Okay, why am I so slow at rearranging? This derivative is not super easy. The International Physics Olympiad is the pinnacle of physics competitions around the world. Let's solve an entire problem from it. Okay, this is from the 2024 Olympiad and we'll be looking at the greenhouse effect problem. Very typically we're given quite a lot of information and then we've got a series of questions. I really enjoyed this problem because the solutions are really not standard. Let me show you. So in this problem, we'll examine a simple model of global warming, and then we are given this quantity, U, which is a function of wavelength and temperature, and this quantity indicates the thermal radiative power per unit area. Okay, power per unit area, this is essentially intensity so far. And we're given the famous Planck's law formula over here. Ah, look at this, absolutely beautiful. We're given hc by itself in some kind of non-standard units, electron volts, Newton meters. We're given Boltzmann's constant, once again some relatively non-standard units. The wavelength corresponding to the maximum of lambda t comes from the relation lambda max times t is equal to b. This here is Wien's displacement law. We'll actually be deriving this one. I normally just teach it, but now we get to derive it. Okay, and we're given this ton of information. Now let's just see what this first question is asking us. Well, A1, find the solar constant S0. Okay, we probably skipped somewhere in the question when this thing is defined. So, throughout this problem, assume that the sun is a black body at its average surface temperature. Okay, the sun's radius is this much. We're given the astronomical unit over here. We denote by tilde US the spectral solar power radiated into a unit area of the Earth. The integral of this quantity over all wavelengths S0 is called the solar constant. So S0 is the integral of this d lambda. Now, the International Physics Olympiad is not really a maths competition, so I really doubt we're going to have to integrate this beast over here, especially for the first problem. What this question is really asking us is, can we figure out the solar power radiated per unit area from the sun where the Earth is across all the different wavelengths? Okay, let's get on to this. So this is part A1. I'm going to treat this quantity S0 just as regular intensity. I'm going to say that S0 is just equal to the power produced by the sun divided by the surface area of a sphere starting from the sun and then reaching where the Earth is, which is just 4 pi d squared. Relatively standard intensity problem. To work out the power of the sun, we can just use Stefan's law, which says that the power of the sun is just equal to 4 pi times the radius of the sun squared, then Stefan's constant multiplied by the temperature of the sun raised to the power of 4. And then we need to divide this by 4 pi d squared. And look at this, the 4 pi's are just gonna cancel out. Don't you just love it when that happens? I don't know, it kind of looks like I cancelled out the radius of the sun as well. So let me just try again. That's a bit better. I think we've got all the values to actually plug in. So the radius of the sun, well, this here is just equal to, where was it? It was definitely given in the question. 6.96 times 10 to the power of 8. And then we have to square that, multiply this by Stefan's constant, which if memory served me right, 5.67 times 10 to the power of minus 8, multiplied by the temperature of the sun, which in this case is given up to 5.77 times 10 to the power of 3 Kelvin, raised to the power of 4. And then we are going to divide this by d, where d is just the distance between the Earth and the sun, and then square that. We're not going to forget the square. So what is that? 1.5 times 10 to the power of 11 squared. And now my all-time favorite thing, which is to be plugging things into a calculator. I'm actually being sarcastic. I don't really enjoy plugging things into a calculator. I prefer symbols. How about you? Let me know. And we're going to get a grand total of 1353, and that's watts per meter squared, isn't it? The question asked for 3 significant figures, so let's just say that this here is 1350 watts per meter squared. So far, so good. So let's check out number 2. We want to find the temperature of the Earth. Hang on, can't I just like take a thermometer and measure it? That is nowhere near as fun as solving equations and calculating it. The way we're going to do this one is by assuming that the Earth is a perfect black body radiator. So what does that mean? It means that it's going to emit perfectly the amount of power that it has actually received. So for A2, what are we going to say? We're going to say that S0 was equal to the power that's been received but also emitted divided by the area over which this thing was received. But also the power, let's say, received is equal to the power emitted, and this thing here will be equal to Stefan's constant, the surface area of the Earth, quite large, and then multiply by the temperature of the Earth as well, raised to the power 4. I think that's right. So let's plug this back into here. What are we going to get? We already have a numerical value of S0. So we get that S0 is equal to Stefan's constant, the area of the Earth. I'm just going to call that AE, multiplied by temperature of the Earth. Let's call that T subscript E as well, raised to the power of 4. Okay, divide that by the area which has been received. Okay, now here's something really interesting. So the cross-sectional area that receives the sunlight, because all the rays are actually parallel, is actually a circle. So for the area that receives the sunlight, you can think of it as a disk. Imagine flying towards a uniform sphere. You wouldn't be able to tell whether you're looking at a sphere or not, provided there's no lightning and features and all this stuff. So AR is actually going to be pi r squared. On the other hand, the Earth will be emitting all of this uniformly. So this means that for the area of the Earth that's emitting all that radiation, we're going to just use 4 pi r squared. So in practice, this thing here will be equal to this constant. The area of the Earth is 4 pi, radius of the Earth squared, temperature of the Earth raised to a power 4. Divide that by AR, which is a circle, which is going to be pi RE squared. And look at this, we can get rid of the pi's. Although I'm getting kind of hungry, I wouldn't mind a pie. Get rid of r squared. Okay, this is not looking bad. So, let's rearrange for the temperature of the Earth. The temperature of the Earth is going to be the 4th root of, okay, why am I so slow at rearranging? So what would that be? S0 over 4 multiplied by Stefan's constant, which is going to be, let's use 1353 to avoid any rounding errors. 4 times 5 point, oh, this here's the 4th root. Do not forget the 4th root, kids. 5.67 times 10 to the power of minus 8. Let's see what this gives us. So this here gives me 277.9 degrees. Should we just call it 278 Kelvin, like so. The answer kind of makes sense. Okay, on to the next one, A3, which I think is one of the most difficult questions in the actual paper, just because it's so hard to actually visualize what this question wants. So you're going through some things which are pretty standard, sort of the Earth's temperature, intensity, and then it's suddenly find the function f of x. Well, what is this f of x? Let's go back to the actual question. So what do we see? Okay, the wavelength corresponding to the maximum of u lambda t comes from the relationship lambda max t is equal to b, v is displacement load. Indeed, using equation 1 can be shown that b is hc over xm over kb. Okay, the first thing that I'm going to do for A3 would be simply to rearrange for x xm. I'm just gonna calmly write b is equal to hc over xm, Boltzmann's constant. Then what does that mean? Well, xm is just going to be equal to hc over bkb, but we also know that the value of the constant b is just equal to lambda max times t. So this here is hc over lambda max multiplied by t multiplied by Boltzmann's constant. Now, there's something here which can be initially confusing in this problem, and that is, what does this subscript here actually mean? Well, this value of x will depend on the wavelength, because you can see the wavelength right here in the equation. So there will be a value which corresponds to the maximum wavelength. And this is exactly what this subscript here means. It means the value of x that corresponds to the maximum wavelength. Wait, did I say a maximum? You know what that means? It means we're gonna need to do some differentiation, which I absolutely love because I love calculus and I love applying it to physics problems. Let's do it. So my plan of action would be to take the quantity u, and I'm gonna do du of lambda t. I'm gonna differentiate this with respect to lambda, and I'm gonna be setting that to 0. This derivative is not super easy. I mean, you can do it with a combination of the quotient rule and then also the chain rule, but I'm gonna show you a much easier way if you've covered this, and I learned this from the Feynman lectures on physics. Almost nobody differentiates in this way, which is super interesting, but it makes these derivatives quite a bit easier. So let me show you the process on how to do it. So we want to figure out the derivative of this big complicated thing. So d by d lambda of, tell you what, let's just take the constant outside of the derivative sign. So what is that? 2 pi hc squared. And then I'm going to do d by d lambda of whatever is left over here, 1 over lambda 5, and then times by 1 over the exponent of hc over lambda kb, and then multiply this by t, divide it by, take away 1, like so. So how does this differentiation actually work? I absolutely love this method because it saves me quite a lot of time in situations like this. The first thing that we want to do is quite simple. We just need to rewrite the expression. Then we're gonna open up some big brackets, and then for each term that contains the variable that we are differentiating with respect to, in this case lambda, we are going to have a separate term, and we're going to start this with the power of this actual term. For this case, because we're dividing by lambda to a power of 5, our power is just -5. Then in the denominator, we're just going to copy our function, which is lambda to a power of 5, and at the top, we're just going to differentiate it. So the derivative of lambda to the power of 5 with respect to lambda is just lambda to the power of 4. Then we're going to add our next multiplier. So this here is going to be plus. Now, the one here we can ignore because this derivative will end up being 0, but the exponent of this has a power to the -1. So we're just going to have a little -1 over here. Once again, in the denominator, just copy your expression. So this here is just the exponent of hc over lambda kbt, take away 1. At the top, we need to differentiate our expression. So the derivative of e to the x is, well, we're going to have to use the chain rule for this one. So this here will just be the exponent of hc over lambda kbt. The 1 disappears, and then the derivative of the inside function. So these are just constant, aren't they? So this here will be hc over lambda squared with a negative sign here, kb, and then t. Now the two negative signs here are going to turn into a plus. And this here is actually our derivative, and that did not take very long. I think this is so much quicker than using the combination of the chain rule and then the quotient rule. Okay, so let's set this derivative to be equal to 0. But just before we do that, so we know in the previous part of the question, we know that xm is equal to hc over lambda max tkb. So as long as this derivative here is set to 0, all of these turn into lambda max. And what we spot over here is that if we do a little trick, and this is really cool, we're going to take a factor of 1 over lambda to the power of 6. What do I mean by that? So this here will end up just leaving me a factor of 1 over lambda. And this here was to the power of 5. So let's extract from the bracket a factor of 1 over lambda. So then I'm just going to write this in red over here. 1 over lambda to the power of 6. Then 1 over e to the hc over lambda kbt, take away 1. And then in the brackets, we're just going to have minus 5. We've taken that lambda onto the other side. So what we're going to be left with is hc over lambda kbt. No longer lambda squared because we've taken a factor of 1 over lambda out. The exponent of this, hc over lambda kbt, divided by the exponent of hc over lambda kbt, take away 1. And when we set this equal to 0, this is going to correspond to the maximum wavelength, so we can essentially call these lambda maxes. Right, this thing can only be equal to 0 if this here is equal to that. But also, we're going to remember that xm is actually just equal to hc over lambda lambda max kbt, like that. So what we can say is that this here has to equal to 0, so minus 5 plus. When this thing here turns into lambda max, when the derivative is set to 0, this will turn to hc, well, that's just xm, e to the power of xm divided by e to the xm, take away 1 is equal to 0. And look how nice and simple that sort of looks like. Well, we're going to have to solve that in a minute, and trust me, it won't be so simple. Okay, so what does that mean? It means that 5 is equal to xm e to the xm over e to the xm, take away 1. Now let's bring this over here. 5 times e to the xm, take away 1 is equal to xm e to the power of xm. Let's make xm the subject, so we're going to divide everything by e to the power of xm, so we're just going to get 5. We can just do this, e to the xm, because this here is going to be a separate term. Take away 1 over e to the xm is equal to xm. What is that going to give me? 5. 1 minus e to the minus xm is equal to xm. In other words, 5, 1 minus e to the minus xm, take away xm is equal to 0. Well, this here is our function f of x that we're actually looking for. Now this question actually makes sense, because what it says over here is that the dimensionless quantity x subscript m is the non-trivial root of an equation of the form f of x is equal to 0. This here is that equation. Now, I'm not gonna lie, our celebration is kind of short-lived, because what we actually need to do is find an expression for xm now, which is tricky. Now, the annoying thing is because I've basically memorized a lot of the constants, so xm is equal to hc over lambda max, k, b, and t. Even though we've not really calculated lambda max, I know Wien's law, but this question kind of like derives it. So memorizing constants is nowhere near as fun as solving these equations. So how do we solve these equations? Now, any mathematicians out there, please tell me that I'm not wrong, that this thing here has no real solutions, because we get this 5, 1 minus e to the minus xm is equal to xm. This here is a transcendental equation. The best way to do this is actually really interesting. So all we need to do is pick our required precision. In this question is just 3 significant figures. So what we're actually doing is we're taking a number which is 5, and then we're taking that number multiplied by an exponential which dies off really rapidly, and we want it to be equal to x of m. So we start off by guessing. A really good initial guess is that this number here is very, very small. Then we're doing 5, 1, take away something really, really small. So that should give us roughly the same number here, 5. Well, let's see what that gives us. So assume x of m is equal to 5. This is actually the method that's also given in the mark scheme. Do let me know if you can use a different approximation method to produce more or less the same result. I'll be very interested to hear that. So then we'll just do 5, 1 minus e to the minus 5. And what does that give us? This here gives me 4966, so let's call it 4.97. Now, in this iterative method, then this here then becomes your guess, and then you keep going until you find more and more digits. So then we are going to assume x of m is equal to 4.97, and then we do 5, 1 minus e to the minus 4.97. We stop with this until the actual digit doesn't change, so let's just change that to 4.97. Close enough, 4.965, up to 3 significant figures. This is also 4.97. So this here is our winning solution up to 3 significant figures. Oops, I've just spotted this here should have been A4 actually. But now let's move on to A5. So for A5, what do we actually need to do? We need to find lambda max for the Sun and the Earth, only for 0.2 marks. So now we've actually got all the values, which is absolutely perfect. We've got xm, we have hc, and we have the temperatures, and we have Boltzmann's constant. So all we need to do is take this equation that we've already looked at, and then calculate the 2 maximum peak wavelengths. Not too bad for 0.2 marks, eh? We actually now get to calculate Wien's constant. I know probably in the real exam I would have just rearranged this for lambda max straight away, but I do kind of want to get that number for Wien's constant, which is going to be a lot of fun. Okay, we have some non-standard units over here. So hc is, what is it, 1.24. Multiply this by 10 to the power of 3 electron volts, and then nanometers. Then multiply this by, divide this by 4.97. Then Boltzmann's constant is given as 8.62 times by 10 to the power of minus 5 EV k to the minus 1. Very interesting units. We can get rid of the EVs by cancellation. And now let's plug this into a calculator. Yet again, our trusty calculators are getting quite a lot of work done. 1.24 times 10 to the power of 3 divided by 4.97 times by 8.62 times 10 to the power of minus 5. This here is going to give me 2.894, let's call it 2.89 up to 3 significant figures times by 1, 2, 3, 4, 5, 6 times by 10 to the power of 6 nanometers k to the power of -1. Let's convert this to meters, so this will be times by 10 to the power of -9, which is going to give me 2.89 times by 10 to the power of -3 m k to the -1. And we have successfully derived Wien's constant, which I've been teaching for ages, but it's always really nice to see where it comes from. Okay, now to actually calculate lambda max. So let's start off with the sun. Lambda max will be equal to this constant, 2.89. There's a dot here, it's multiplied by 10 to the -3. Let's rewrite that 3, shall we? And then divide that by temperature of the sun was given as, let's see what it was given as. It was given as so much information, 5.77 times 10 to the power of 30 Kelvin. 5.77 times by 10 to the power of 3. Let's see what we get. So this here gives us around 5.01, let's call it. Multiply this by 10 to the power of -7 meters within the visible range. Makes sense. Let's do the same for the Earth. Lambda max is equal to the value of the constant, 2.89 times by 10 to the power of -3 divided by, what was the temperature of the Earth? We calculated it all the way back here somewhere. 278 Kelvin, 278, giving us around 1.04 times by 10 to the power of -5 meters. Okay, so this here is outside the visible range, which makes sense. You know, at night the Earth is not glowing, at least in the visible range, but it will be emitting some infrared radiation. Okay, on to the next one, A6. In figure 1, the functions gamma, u tilde as gamma, and u are plotted versus gamma, where gamma is a dimensionless coefficient to rescale. Oh, I don't really enjoy rescaling, to be honest. Such that the values of the two peaks coincide to determine gamma. So this question is kind of convoluted. It takes a little while to actually realize what is happening. But all this is trying to say is that here is this figure, and we've changed the spectrum of one of them so that the two peaks have exactly the same value. And what we have actually are some equations over here, and we can plug in lambda max for those and then rescale them. Notice though that one of them here is known as u tilde s on top rather than just u. So what was the difference? Okay, so u with a tilde on top is the spectral power radiated into a unit area of the Earth normal to the direction of the radiation. And this is what makes this question just so incredibly hard in my opinion, because these things are so easy to actually get missed. So to explain it really well, what we must say actually is just define those things, even write them in words if you have the time, but u with a tilde s is going to be the normal proportion of the radiation that's been received throughout the surface of the Earth. And since US is the power per unit area emitted by the body, to get the entire power by the sun, we must multiply by the area, which is going to be 4 pi r of the sun squared. And then to get the proportion which is received on the Earth, we must once again use the fact that intensity is inversely proportional to the distance squared. So what we must do is divide by 4 pi d squared. And this is so incredibly tricky to miss. At least for me, I find it tricky. Let me know what you think. We can cancel out the 4 pi's. So what we get for u tilde s is that it's just equal to r of the sun over this distance squared multiplied by us, which is all of this 2 pi hc squared over lambda to the power of 5, 1 over the exponent of hc over kb lambda t take away 1. Our scaling law simply means that the two peaks are just going to coincide. So we can say that gamma u tilde s is going to be equal to u lambda max as a function, what do they call it, e t. Okay. And this here is going to be evaluated at lambda max. Shall we just kind of like write this over here? Okay, so we're looking for gamma. So all we need to do is basically write out u as applied for the Earth as an emitter and then divide it by this expression. Now those constants terms of 2 pi hc squared, they're all going to cancel, so I'm not going to be writing them in. Remember, for u tilde s we have this factor which is r sun over d squared. This here is the maximum wavelength. Okay, 1 over lambda sun max, so many subscripts, something like that, raised to the power of 5. 1 over the exponent of hc over, I'm just going to write lambda s because I'm running out of space, kbt, take away 1, something like this. Okay, now this here looks awfully complicated, but we've got a trick up our sleeve. Lambda max times the temperature is always a constant, no matter what. It's 2.89 times 10 to the power minus 3. That's just Wien's law, isn't it? So this means that this quantity, lambda max times t, is exactly the same as this quantity, like so, which means that we can just do this grand cancellation across here. We're going to be left with a much simpler expression. So let's tidy this expression up. So that's going to give me 1 over, that is equal to 1 over lambda max e, what is that? Right, more putting stuff into the calculator. And this here gives us a grand total of 0.0120499, etc. Let's leave it as that as our scale factor. Yay! Now we're going to be looking at the actual greenhouse effect. So we introduce a simple model in which the Earth's surface is modeled as a thin layer. We have once again quite a lot of information. A couple of very important assumptions are given though. So we're going to assume that the atmosphere layer reflects a fraction Ra of the incoming radiation, which is 0.255. It gives it as a fraction of the visible ultraviolet radiation, but I am pretty sure that we have to assume that that's over from the entire spectrum in order to be able to solve this, but we'll see in a minute. Okay, assume that the atmosphere does not reflect any part of the infrared radiation, however it absorbs a fraction and then transmits the rest. This behavior, known as the greenhouse effect, changes the average temperature of the Earth, and we've got a nice little diagram here of the greenhouse effect. Okay, B1, we're going to assume that E is equal to 1. Now what was E? So E is the fraction of the infrared radiation that's been absorbed by the atmosphere. None will be reflected from the Earth, and I want to calculate the Earth's temperature and the atmospheric temperature TA. So anytime you want to calculate temperature, you have to use Stefan Boltzmann's law in those types of problems. The easiest way is just to assume a thermal equilibrium, and what we can say is that the total power that's been incoming into the Earth will be equal to the total power that's transmitted back from the Earth. So Right, let's write this out. So for B1, the total power that's being transmitted by the Earth, what is that going to be? 4 pi, radius of the Earth squared, Stefan's constant, the temperature of the Earth raised to the power of 4. This here will be equal to the total power that's coming from the Sun, but now some of it is going to get reflected. So earlier we calculated the coefficient S0, which is going to be really, really useful. We did that in part 1, the solar constant. That is the spectral power radiated per unit area. And I think this is one of those things that makes this question just so much more difficult, because there's just so many little things that can sort of catch you out in this relatively non-standard problem. So the total incoming power is going to be equal to S0, which is a solar constant, but that was per unit area, and the cross-sectional area for the incoming light was that of a disk. So that's going to be pi RE squared. But of course, we're now going to have some of it which is going to be absorbed. So how much is going to be left? Well, it's going to be the total one, take away the fraction, which is our atmosphere, RA, and then S0 pi RE squared. And that's not even the entire equation, because I've hardly got space to write the other one, but what we must also consider is the atmosphere, because the atmosphere is now going to reflect back some of that radiation as well, because it has a temperature. It has to have a temperature and just radiate backwards. So let's see if I can fit this on this side. So it's going to be plus 4 pi RE squared, assuming that the atmosphere has the same radius of the Earth. In fact, it's going to be a little bit bigger. And then Stefan Boltzmann's constant, and then the temperature of the atmosphere raised to the power 4. This here is the temperature balance for the Earth. What we also need to do is consider the temperature balance for the atmosphere. And here is something really tricky. It actually says that in the question. So in order to solve this problem, we must be really, really careful with how we spot things. So what does it say? Assume that the atmosphere layer reflects a fraction from above or below and completely transmits the rest. So that means that the atmosphere will be radiating both into space and also back onto the Earth. We can say that 4 pi RE squared, this temperature of the Earth raised to a power of 4, has to be equal to 2. And then the surface area of the Earth, I should have just called this A, RE squared this. Now the temperature of the atmosphere raised to a power of 4. And now we are in good territory, because we have 2 equations and we have 2 unknowns. All we need to do in this question, if I remember correctly, let's see, is to figure out the temperatures TE and the temperature TA. Okay, so that took me way too long to think, but all I'm going to do is I am just going to substitute this back into here, and then I'm just going to solve the equation. So what am I going to get? I am going to get 2 times 4 pi RE squared, Stefan Boltzmann's constant, TA to the power of 4. That is equal to, let's take a factor of S0 pi RE squared. And then what are we going to be left with? We're going to be left with 1, take away RA, like this, plus 4 pi RE squared constant TA to the power of 4. I feel I'm getting tired a little bit. So, right, we're just trying to figure out what TA is. Now what I'm going to do is take this and take away this term. So we're just going to be left with 4 pi re squared. This ta to the power 4 is equal to s naught pi re squared 1 minus ra. And then let's just divide by pi re this. Ooh, we can't get rid of Stefan's constant just yet. Okay, like that, like that. And then we're going to be left with that TA will be the fourth root of S naught 1 minus RA over 4 times Stefan's constant. Let's see what that gives us. Okay, back to our trusty calculator. I think we've actually calculated all those values from before. Okay, so I'm going to need the fourth root of fraction S naught. What did we get for S naught? And this here is going to give me around 258 Kelvin. Perfect. We've got the temperature of the atmosphere and probably sounds about right. Now what we're going to do is see if we can calculate the temperature of the Earth. So in our previous calculation for the temperature of the Earth, we're basically assuming that there was no atmosphere, that it was receiving some radiation, that was emitting it perfectly. And if that's the case, life on Earth would have been pretty cold because we got, what did we get? 277 or something like this for the temperature of the Earth before. But luckily for us, we have atmosphere. So the temperature of the Earth, I'm just going to use equation 2 for this. So from equation 2, I can essentially just get rid of this like that. And let's just write this. So from equation 2, we are going to get Te to the power 4 is equal to 2 Ta to the power 4. Temperature of the Earth is going to be equal to the 4th root of 2 times 258. Let's see what our trusty calculator gives us one more time. Oops, I missed a power 4 just here. This here gives me 306.8, let's call it 307 Kelvin, which is pretty close to standard temperature. Well, sort of standard. I live in the north of England, so we are lucky when we have 307 Kelvin. Okay, folks, I think we're going to finish the video there. This problem is highly fascinating, but this video is getting just way too long. And I hope you've really enjoyed this, and you should definitely check out yet another amazing problem from the International Physics Olympiad that you must absolutely watch. Check this out, click over here.